Hello, AP Chemists. So we're going to start talking about electrochemistry, and to do these conversations, we're going to work with the notes that we have for our electrochemistry unit, and you can download a PDF copy of the notes through Schoology. And so you can see here page 1 of the notes, and the conversation we're going to get into in some detail here is going to be on the idea of oxidation number. But before we talk about oxidation number, we've got to make some definitions. So I'm going to go ahead and zoom in on the worksheet here, zoom in on the notes, and you can see the first two things we have to do is define oxidation and reduction. The fundamental thing you have to keep in mind is that electrochemistry is all about the movement of electrons. Right? So something's going to have the electrons and something else is going to want the electrons. And so we're going to be talking about transferring electrons from one species to another. And as that transfer happens, something is oxidized and something is reduced. So that gets us into our definitions here. Oxidation refers to the process of losing electrons. And the phrase we would use is the species that loses the electrons is said to be oxidized. So as it's giving up the electrons, it is becoming oxidized. Reduction refers to gaining electrons. And so the material that is receiving the electrons is said to be reduced. Now, what's actually going on here is we're going to be tracking this process using an idea referred to as oxidation number. And you can see that as our first main topic here, oxidation number. Now, we've seen a related concept to oxidation number, and that is the idea of formal charge. We've seen that when we were talking about Lewis dot structures and how we could possibly evaluate the quality of Lewis dot structures. So what I'm going to do is I'm going to make a little bit of a comparison. I'm going to remind you what formal charge is all about and then describe for you how oxidation number is similar but importantly different. So to do this, let's talk about a simple molecule like water, H2O. And of course, water has the following structure. Oxygen in the middle, some lone pairs on the oxygen, and we have that structure there. And of course, it's bent. Now, we talked about back when we were doing Lewis dot structures, how we could go ahead and calculate formal charge. So I'm going to do the formal charge calculations here in black ink. So for example, we could do the formal charge of the oxygen. And remember, you start with the group number, and oxygen is in group 6. And then you count the number of electrons around it. So we have 1, 2, 3, 4 electrons from the lone pairs, and then as you'll recall, you take the bonding electrons and you split them in half. One goes towards the oxygen, the other goes towards the hydrogen. So what we then would have is a total of 6 electrons being around the oxygen. So we would subtract those 6 electrons, and the oxygen would have a 0 formal charge. Then we could do the formal charge of the hydrogen. Hydrogen is, of course, in group 1. The electrons in the OH bond get divided evenly, so one of these electrons goes to the hydrogen again, and so then we have the net result of subtracting 1 and ending up with 0. So water has a 0 formal charge on the oxygen and a 0 formal charge on the hydrogen. Let's see how we do the idea of determining oxidation state. It's a slightly different method, and I'm going to go ahead and do this calculation in red. So the oxidation state, the OS of oxygen, we start the same way. We're going to start with the group number, which is 6, but then we count the electrons a little bit differently. As before, the lone pair electrons get counted only towards the oxygen, so there are 4 electrons to the oxygen from the lone pairs. But then, when we talk about the bonding electrons, this is an entirely give-and-take situation. And so the more electronegative atom will take all of the electrons involved in the bond. So the oxygen here is going to take both of these electrons and both of those electrons. So now this oxygen, in terms of accounting for oxidation state, has 2, 4, 6, 8 electrons around it. And so when we do this math here, it's going to be 6 minus 8 for for an oxidation state of -2. The oxidation state of the hydrogen, then, we would calculate as starting with the group number 1 minus how many electrons are around it. And remember, the hydrogen actually lost out to the oxygen because it's less electronegative. So these bonding electrons are only being counted towards the oxygen, so the hydrogen is behaving as if it has no electrons around it. So that's 1 minus 0 for a total of +1. So there are similarities in that you start with the group number for both calculations. The difference is in how you count the number of electrons surrounding any one particular atom. Now, another commonality you should have picked up on is that the sum of the formal charges, for example, 0 and 0, right, that adds up to 0, which accounts for the total charge on the molecule, right? Water is neutral, so it has a 0 charge, and that the total charge accumulated from the oxidation state also will add up to the total charge of the molecule. So the oxygen has a charge of -2. Both hydrogens have a charge of +1, so that also adds up to 0. So the sums of the formal charges have to add up to the overall charge on the species, as does the sum of the oxidation states has to add up to the total charge on the species. All right, so that's kind of in general how we calculate oxidation state. And if we take that general idea and start applying it to particular atoms in their most common situations, you'll start to see that we can develop some general rules. All right, so I'm going to shrink this calculation down, kind of move it out of our way, and bring back our notes, zoom in on our notes. And so what we have in the next few bullet points are some common rules for different types of atoms. So I'm going to pick up here with this first bullet point. In most of its compounds, the oxidation number of oxygen is going to be -2. Now, why is that? That's because oxygen's pretty electronegative, as we just saw with water, and so when oxygen tends to be bound to other atoms, it tends to take all the shared electrons, and then it only needs 2 electrons to complete its octet, and so it's going to typically have an oxidation state of -2. One typical exception to that is hydrogen peroxide. And the reason here is, and maybe I'll zoom in a little bit to draw this, hydrogen peroxide has a general structure that looks like this. The key idea being is that we have an oxygen-oxygen bond. And so when you have electrons shared between identical atoms, just like in formal charge, here, since there's no electronegativity difference, when we account for the electrons for oxidation state, one electron is going to go to the left oxygen, one electron is going to go to the right-hand oxygen. And so they're dividing those bonded electrons evenly. The net result is that you will eventually do a group number of 6 minus 7 in terms of the number of electrons around it. So each oxygen will have a -1 oxidation state. Okay, so let's keep on going and looking at some of these other rules. In most of its compounds, hydrogen is going to have a +1 oxidation state. Hydrogen is not very electronegative at all, so in the competition for the bonded electrons, it's going to lose out to just about all of the main group elements at least. And so its most common oxidation state is going to be +1. But now, on the flip side, it turns out that hydrogen is more electronegative than just about all of the metals. In fact, I can't think of an exception here. So if hydrogen is combined with a metal, then it's going to take the electron density from the metal, and it's going to end up having the oxidation state when it's bonded to metals. It's going to form a hydride, which has an oxidation state of -1. Just kind of like the halogens when they're charged, right? Fluoride, chloride, bromide, they all have a -1 charge or oxidation state. So when hydrogen is in a compound connected to a metal, it's going to take the electrons and have an oxidation state of -1. So there are 2 elements, oxygen and hydrogen, for which we're going to have pretty consistent results in terms of assigning oxidation states. So once you have the oxidation states for some atoms, you can start to develop the oxidation state of all of the atoms in a compound. And I should make real clear at this point that just like formal charge, oxidation state is a property of the atoms in the molecule. A molecule doesn't have an oxidation state. A molecule has perhaps an overall charge, often 0, but molecules don't have oxidation states. The individual atoms within the molecule will have the oxidation state. All right, so we can look at some quick little examples here. For example, HCl. Hydrogen here is with a nonmetal, so it's going to lose out, so its oxidation state is +1. And then chloride is going to be -1 because the whole compound is neutral, so again, the sums of my oxidation states have to add up to 0. Here's sodium hydride, so the sodium will be +1. Here's hydrogen with a metal, so it's got to be -1. Here's a slightly more complicated compound. This is called lithium aluminum hydride. So the hydrogen's going to be +1. Each of the hydrogens will be, whoops, I made a mistake there. Let me back up. Each of the hydrogens is going to be -1 because the hydrogen is with aluminum. So that's going to be -1. And then the one lithium is going to be +1. So what you're starting to see is that things like metals and things like the main group metals like lithium, sodium, potassium, or in group 2 magnesium, calcium, and strontium, their oxidation state is going to be identical to the charge they would have as an ionic species. The same is going to be true for the halogens, fluorine, chlorine, bromine, iodine. They're going to have a -1 oxidation state. So now as we take a look at lithium aluminum hydride, we can actually do a little bit of a calculation here. So each of the hydrogens is -1, but I have 4 hydrogens. So that tells me I have a total charge contribution of -4 from all of the hydrides. I have just 1 lithium, which is charged +1, so we have a total of +1 charge from all of the lithium. Now, since lithium aluminum hydride overall is going to be a neutral molecule, then the total charge here has to add up to 0, which means the aluminum has to bring a total of +3 charge to the compound, and there's only 1 aluminum, so it itself has a +3 oxidation state. And these numbers right here, those are the oxidation states. The numbers up here, that's the total charge brought by the combination of those oxidation states per atom, but the stuff in the red oval, those are the individual oxidation states of the atoms in the compound. All right, let's take a look at some other examples. For example, SO4 2-. If we do a similar kind of calculation, we've learned that oxygen has an oxidation state of -2. There's 4 of them, so that gives me a total of -8. Now, the SO4 2- species has to have a total charge of -2. So the sulfur must bring +6 to this charge party. There's only 1 sulfur atom, so it itself has the oxidation state of +6. And so again, those numbers in the red oval, those are my oxidation states. All right, sliding over and taking a look at NO3-. Oxygen's -2 for a total of -6. I have a -1 charge overall, so the nitrogen has to bring +5 to the party. There's 1 nitrogen, so it has an oxidation state of +5. So again, those are my oxidation states. HBr, this one's pretty quick and pretty easy, so that's going to be +1 for the hydrogen, -1 for the Br. NaH3, +1 for the hydrogen because it's with a main group element, so it's going to lose the electrons for a total of +3. Ammonia is neutral, so the nitrogen has to bring -3 to the party. There's 1 nitrogen, so its oxidation state is -3. Okay, so as you see, I'm starting to pick up steam here and starting to do this a little bit more quickly, and this is the kind of practice that you're going to have to get into. Assigning oxidation states is going to be the first step of a multi-step process that we're going to do when it comes to balancing reactions that involve oxidation and reduction. Balancing those reactions can be a little bit tricky, and we're going to teach you how to do that a little bit later. Okay. Some other rules here. The oxidation state of an atom in its elemental form is going to be 0. Things are going to be sharing electrons evenly. So both hydrogens of H2, both oxygens of O2 are going to have an oxidation state of 0. Elemental iron, since it's not sharing its electrons with anything, is going to have an oxidation state of 0. And we already saw this idea, but the oxidation state of charged species, of monatomic charged species, will be their most common ionic charges. So Cl minus, Ca plus 2, S2 minus. All right, so let's get into a couple of more complicated examples. I'm going to zero in here on this lithium vanadium oxide compound. So the oxygen is, zoom in a bit more, -2 for each oxygen. Let me go back to sticking in blue here. So -2 for each oxygen, total of -6. The lithium is going to be +1. There are 2 lithiums for a total of +2. This compound overall has no charge, so that means the vanadium has to bring +4 to the party. There's 1 vanadium, so that 1 vanadium brings +4. So there are my oxidation states. Iron phosphate. So each oxygen is -2. So there's 4 oxygens in the PO4, and so that brings a total of -8. Then we have the phosphorus. And so now we've got to be careful here, right? Because PO4 has an overall charge. Each PO4 is going to have a 3- charge. So that must mean that the phosphorus is +5, because my total charge of the PO4 just taken by itself is -3, okay? And then since the PO4 is itself -3, and I have 2 of them, then what could I figure out in terms of the oxidation state of the iron? Well, I've got 3 irons, so then each individual iron must bring +2 to the party. All right, so that is a total of -6 from the PO4, from both PO4s. Then I have to generate a total of +6 from the 3 irons, so each iron must itself be +2, okay? And then we have something like potassium permanganate. So again, the oxygen -2, there's 4 of them for -8. The potassium is going to be +1, there's 1 of them for +1. The whole compound is neutral, so the manganese must bring +7. So the 1 manganese itself must be +7. Okay, so they're my oxidation states. Al2SO3, okay? So again, we can kind of divide this up into 2 problems if we wanted to. So we have the aluminum part and we have the SO3 part. All right, so we could do this individually or we could do it all together if you wanted to. But I'm going to leave that one to you. Go ahead and try to figure out the oxidation states of the aluminum, the sulfur, and the oxygen and see what you come up with. And if you want to double check your answer, you can go ahead and look it up if you'd like, okay? All right. So this gets us to a couple of helpful memory tools that we can use. We have a couple of acronyms. We have Leo says GR. These are some sayings that are going to help you remember what's being reduced and what's being oxidized. So loss of electrons is oxidation. So LEO says GR. Gain of electrons is reduction. So this goes back to the definitions at the top of this page. And we also have oil rig. Oxidation involves the loss of electrons. Reduction involves the gain of electrons. So to just help you keep these terms separate and easily identifiable with respect to each other, we have these mnemonic devices, Leo says GR and oil rig. All right, so that introduces electrochemistry. There's going to be a practice quiz for you to work with to double check to make sure you're getting good at assigning oxidation states, because this is going to be the first step you need to lock down in a long series of steps you're going to have to do to be able to balance oxidation reduction reactions. All right, that will do it for now.